Hello everybody, welcome to Part B of Chapter 4.5. The two things we're going to focus on today are using change of variables to evaluate a definite integral. I underlined that because that's the main difference today. And then we're also going to evaluate a definite integral involving an even or odd function, and we'll review what even or odd functions means. To begin, we're going to talk about change of variables. Change of variables. And we'll just kind of formally define that first. We'll say if the function u equals g of x, right? We're going to find a u in these integrals, and then we're going to also say that those u's are going to be g of x's, has a continuous derivative, on the closed interval from A to B, and fancy F is continuous on the range of G, then we can say that the integral from A to B of f of g of x times g prime of x, which is really u and du, dx, equals the integral from g of A, right, u evaluated at A, to g of B, u evaluated at B, for f of u du. Sorry, that u looks a little bit weird, but that is a u there. And let's practice what this means. So let's do an example. Let's say we're given the task to evaluate the definite integral. And we are given the integral from 0 to 1 of x outside x squared plus 1 cubed dx. A couple of things we can determine here. First of all, we should label, remember we talked about yesterday, when something's to a power, that's typically a good idea to make that your u, x squared plus 1, meaning that du is going to have to be 2x, because the derivative of this is 2x. I also want you to say something over here that u equals this, which is also equal to g of x, right? That's part of what we just defined, where u equals g of x. So keep that in mind. Using this as g of x, we can create new limits, new bounds for our integral. Instead of 0 and 1, we're going to throw 0 and 1 into this g of x to find the new limits. So we're going to say g of 0 equals 1 squared plus 1, which is going to be 2. And then we're going to say g of 1 is going to be, 0 squared plus 1 would be 1. And then here, 1 squared plus 1 would get me 2. That's what I meant to say. So the new bounds are going to be 1 to 2. So we have our new bounds, like our new limits, right here. We have u and we have du. Remember from yesterday's lesson, though, since du is 2x and we only have an x, we need to do that 2 and that 1/2 thing. So when we write our whole new integral, we're going to write it with the new limits, and we're going to write it in terms of u and du. So we're going to say the integral from 1 to 2, right, new limits. And now we're going to say 2, or 1/2 times 2x, right, now we have a du, times x squared plus 1 cubed dx. Okay. Oh, this is a dx up here too. Okay. Now we can start to substitute everything out. We already put in our new limits, and now we can call the 2x dx the du, right? That's what those parts are becoming. And remember, we had x squared plus 1 as our u. But since it's cubed, we also have to make it u cubed. And then we have that integral from 1 to 2, and we put the 1/2 out front. Sorry there's so much space there. There shouldn't be. It should just be u cubed du. Okay. And we can go from here. We can find the antiderivative. So we're going to say 1/2 outside the antiderivative u to the 4th over 4. And we're doing that from 1 to 2. So that's the same as saying 1/2 outside of 2 to the 4th over 4, 16 over 4, minus 1 to the 4th over 4, 1/4. Okay. And when I finish that out, I get 1/2 outside 4 minus 1/4. So I get 1/2 outside of 15 over 4, right? If I did 16 over 4 minus 1, I get 15 over 4. Which gets me 15 over 8, and that is my answer. All right, let's try another one. It's always fun to do more than one example. Again, our task is to evaluate the definite integral. Okay. And this one is a little bit more fun. It's the integral from 1 to 5, and we have x on top all over radical 2x minus 1 dx. I want you to recognize that the thing with the power here is actually 2x minus 1 because it's 2x minus 1 to the 1/2. So that's what we're going to make our u. We're going to say u is 2x minus 1. Now, I want you to understand something else. In here, the derivative of u right now would be just a 2, but there's really no way that I can make the x into a 2 using that coefficient thing that we've learned before. I can't do like a 2 and a 1/2 or a 3 and a 1/3 or a 4 and a 1/4 to get a du that I need. So I need to manipulate this kind of a different way. I need to set this up and solve it for x. So I can replace this x in terms of u. And here's what I mean. U is 2x minus 1, that's true. Oh, excuse me, radical 2x minus 1. That's what I need to change. U is radical 2x minus 1. And remember, that's also equal to g of x, right? So we can get our limits later. And now let's solve this for x. So if I went through solving this, I'd have to square both sides. And then I'd get 2x minus 1. And if I started to solve for x, I'd have to add 1. U squared plus 1 equals 2x. And then I would find that x equals u squared plus 1 over 2. I'm going to kind of save that for later too, just like I did with my u up there. Okay. Now I want you to realize that I have a way to replace this piece. I can replace this piece by just calling it u. So far that's in terms of u. The x now is also going to be in terms of u. I can replace that x with this stuff right here, and that will be in terms of u. The next thing I need to replace, so I can write it in terms of u, is dx. And I can do that by taking this and taking the derivative of both sides. And then I'm going to be able to solve for a dx. So in order to set that up, I can say dx of x equals 1/2 outside of the dx of u squared plus dx of 1. All right. As I go through each piece here, dx of x is just 1. I have 1/2 outside of ddx of 1 here would just be 0. That would go away. And then right here, ddx of u squared. Remember, I have to kind of use the chain rule because these variables don't match. It's not an x and an x, it's a u and an x. So if I was to take care of the outside, I would get a 2u. And then I would get a times the derivative of the inside. Since the derivative of the inside is just u and the variables don't match, I put the u on top, and I call that du dx. The next fun thing that's going to happen here is the 1/2 and the 2 are going to make each other go away. And I'm going to get 1 equals u du dx. I want to solve for dx, right? So I can replace this dx in terms of u. So I multiply both sides by dx. And then I get that dx equals u du. Awesome. So far I have everything in place, so I can start to substitute back into this integral. However, I need new limits though too. So I'm going to find those new limits by evaluating g of x at these values here, at 1 and at 5. So I'm going to kind of highlight that. My new limits are going to come from g, this, at 1. When I throw a 1 in here, I get radical 2 times 1 minus 1, which is the square root of 1, which is just 1. And then g of 5, I substitute in a 5, and I get radical 2 times 5 minus 1, which is radical 9, and that becomes 3. Okay, so I have each piece that I'm going to substitute in with, and I have my new limits, which means I can write my integral as follows. Kind of down here. Let me zoom this down. Or let me do it actually right here. Okay. So my integral is now going to be from 1 to 3. And I'm going to replace each piece here very carefully. Instead of writing an x, I'm going to write it in terms of u, as I solved for. So I'm going to write u squared plus 1 over 2. I'm going to write u squared plus 1 over 2. And that was all over, right, because x is just this piece. Now, radical 2x minus 1 is actually just u. So I'm going to write u. And then I had times like dx of everything. Well, dx is actually just u du. So I have this whole thing, and then I have times u du. All right. I'm going to write this on a separate sheet of paper so it stays organized, but we're going to work with this. Again, we have 1 to 3, u squared plus 1 over 2, all over u, and that is times u du. And I want you to understand here that since we have a u on top and a u on bottom, those cancel each other out. And then I'm left with a kind of an easier integral, 1 to 3 of u squared plus 1 over 2 du. And furthermore, I can factor out that constant 1/2, and so I get 1/2 outside the integral from 1 to 3 of u squared plus 1 du. When I start to take the antiderivative here, I get 1/2, and then I get u cubed over 3 plus u. And I'm evaluating that from 1 to 3. And so what I end up getting, when I put a 3 into here, 3 cubed is going to be 27. 27 over 3 is going to be 9. So I'm going to have 1/2 brackets 9 plus, and then u would just be 3, minus, if I put a 1 in here, I'd get 1/3 plus 1. Okay. And as we keep going through this, let me find my work here. There we have it. So we'd get 12 minus 1/2 outside, 12 minus 4/3. And when we simplify further, we'd get 1/2 outside of 32 over 3. Right, because 12 over 3, 12 as a fraction over 3 is actually 36, and 36 minus 4 would be 32 over 3. And when I multiply by my denominators, I get 32 over 6. When I reduce that fraction, I get 16 over 3, and that is evaluated. That's as far as we can go. All right, let's try yet another one that does something even more interesting. Again, the name of the game is to evaluate the definite integral. And we are given the definite integral from 0 to 1, x squared outside radical 1 minus x dx. Okay. And now what I want us to do here is actually make the radical piece the u. And we'll go through why that works out the best. We're going to say u equals radical 1 minus x. And I want you to also to remember that this is going to be our g of x that we're going to use to find our limits later. Okay. So u equals this, and we're kind of just going to save that for later. Now, since the derivative of this would just be, well, some really big crazy thing, we're going to use the same approach as last time, where we end up solving this for x in order to replace this x right here. So, when we start to solve this for x, we get u squared equals 1 minus x. I could subtract 1, and then I could change the sign of everything, and I would get that x equals negative u squared plus 1. Again, kind of save that for later. That's going to be useful for us to substitute in. But we have to keep going with it, right? Because now we have something we can substitute in for x. We have something we can substitute in for this radical 1 minus x. But we still need something we can substitute in for this dx over here. And we can accomplish that by taking the derivative of this piece right here. So we're going to do d dx of each side, d dx of negative u squared plus d dx of 1. Okay. As we go through this, we can simplify each thing. The derivative of x is just 1. The derivative of negative u squared. Again, I have to use the chain rule here. So if I took the derivative of the outside, I'd have to put the 2 in front, and then I'd multiply by that negative 1. So I'd get negative 2u. And I have to multiply this by the derivative of the inside, the derivative of just u. Since the variables don't match here, the derivative of u would be du dx. And then over here, the derivative of 1 would just be 0. So that part would go away. Again, I'm interested in isolating dx, so I'm going to multiply both sides by dx. And now I get dx equals negative 2u du. Okay. Those are the 3 things I can use to substitute back in. Now I can rewrite this whole thing in terms of u's, but I need some new limits. So I'm going to write those. I guess I can just keep writing vertically down here. Okay. The new limits we're going to use for our integration are going to come from that g of x, but I need to evaluate at 0, because that was our first bound. And when I do that, I get radical 1 minus 0, which is just going to be 1. And then when I do g of 1, I get radical 1 minus 1, which is going to be 0. So those are my new limits. I'm going to go from 1 to 0. I want you to understand that they're going to look a little bit different. When we write our new integral, this one came first, 1, and then we had 0. That's okay. We shouldn't be changing those around. When we evaluated at 0, we got 1. When we evaluated at 1, we got 0. So that's exactly the way they should look. We can set up the rest of our integral by replacing each thing, right? Instead of writing an x squared, I'm going to square this stuff right here. So I'm going to say negative u squared plus 1 squared. That's like my x squared piece. And then right here, this radical 1 minus x, I can actually just call u. So I'm going to do like a u in parentheses so I know what I'm replacing each piece with. And then dx. dx I'm actually replacing with negative 2u du. Negative 2u du. Alright. We can start to simplify some things here, and I probably will continue this on to the next page. Yeah. So, from 1 to 0, we have negative u squared plus 1 squared times u times negative 2u du. The first thing I'd like to take care of is this u times this negative 2u, which I can turn into negative 2u squared du. And then I still have negative u squared plus 1 squared, and that's still the integral from 1 to 0. Okay. I can expand this binomial here if I square the first thing, so I'd get u to the 4th, and then 2 times both of these things, so negative 2u squared, and then I square the last thing, plus 1. And that's that binomial expanded out. I still have the integral from 1 to 0, and I'm still multiplying by negative 2u squared du. Okay. And I guess what I should really be saying is this, and then brackets, because this is what I'm dealing with. The du is just kind of written at the end. There we go. That's a little bit neater. Lastly, I can distribute this negative 2u squared to everything in here. Or you know what would be a little bit easier is if we just took out that negative 2. So let's do that. Let's take out the negative 2 and put it in front. And then look at our integral that way. So I have a u squared times u to the 4th minus 2u squared plus 1 du. Another step I could take here is to distribute the u squared to everything in this trinomial. So I get negative 2, integral from 1 to 0, u to the 6th minus 2u to the 4th plus u squared du. Okay. And now when I create my antiderivative, I have a negative 2 in front. I have u to the 7th over 7 minus 2u to the 5th over 5 plus u to the 3rd over 3. And that's just following the power rule of antiderivatives. And I'm evaluating from 1 to 0. So remember, when we're using that fundamental theorem of calculus, we take that 0 and evaluate that first. So if I were to do that right now, negative 2 still on the outside, this would all just become 0, right? If I put a 0 on top of all of these, it would just be 0. So I'm going to say 0 minus, now I'm going to put a 1 into this whole thing. So minus a 1 over 7 minus a 2 over 5 plus a 1 over 3. Okay. Now the 0 doesn't do anything, but this negative sign does. I need to distribute that negative to everything here. So I'm going to have a negative 2 outside of a negative 1/7, a positive 2/5, and a negative 1/3. You could go through the common denominator, which would be 105, but frankly this should just be a calculated problem at this point. And when we do all of this inside, we get negative 2 outside negative 8 over 105. Negative 2 times negative 8 here would get me positive 16 over 105. And that is fully evaluated. Okay. Moving on. Alright, there's one last topic I want to go over with you guys, and I'll leave you alone. And that is integration of even and odd functions. Okay. Integration of even and odd functions. In short, if your fancy f is an even function, then we can say the following things. The integral from a negative value a to that same positive value a of f of x is equal to double of that integral from 0 to the positive value, f of x dx. So basically double just the positive half of that integral. If fancy f is an odd function, then we say something else. We say the integral from negative a to positive a of that function is just 0. And I want you to recall what even and odd mean, because I don't know that you would remember that. And I know we last reviewed it like the first week or two of school, so it's been a while. But here's what it means. F of x is even if the following thing happens. When we substitute in a negative x to our function, we should get a positive regular function. Nothing about our signs should change for our function. F of x is odd if, when we substitute in a negative x, we get a negative version of our function. So like all of our signs change for our function. That's what this means. So let's do an example where this will help us and be faster for us than using any other integration properties. So let's say we were asked to evaluate the definite integral and it went from negative pi over 2 to pi over 2, and the function is going to be sine cubed of x cosine x plus sine x cosine x dx. First, we're going to answer the question, is this even or odd? And we can do that by substituting in a negative x and seeing what happens. So that would look like this: sine cubed of negative x cosine of negative x plus sine of negative x cosine of negative x. What this would all simplify out to be would be negative sine cubed x cosine x minus sine x cosine x. I want you to see that the difference between once we substituted in negative x and our original function is that the signs changed. Remember, when the signs all change, that means our function is odd. So, I'm going to kind of write that odd, which means, according to our rules here, from a negative something to a positive that same thing, an odd function is going to be 0. So in short, the integral from negative pi over 2 to pi over 2 of sine cubed x cosine x plus sine x cosine x dx is just 0. I'll draw you a quick graph here as to why. Let me kind of zoom in so I can save some paper here. There we go. That's better. So a quick graph of why this is true. Okay. We're going to call this negative 1 and this 1. We're going to call this negative pi over 4. And then over here we would have negative pi over 2. And then right here we would have positive pi over 4. And then right here we'd have positive pi over 2. And here's what our function would be doing. It'd be going from negative pi over 2, it'd come down to negative 1, and then it would go back up. It would cross through the origin. It would go up to 1 at pi over 4, and then it'd cross again at pi over 2. That's the nice curve we got going on, and I want to illustrate the area that's happening. Over on the right side we have positive area, and over on the left side we have negative area. These two areas perfectly negate each other, right? We have exactly the same positive area that we do negative area, and so they kind of cancel each other out perfectly. And that's what will happen with those odd functions from the same intervals, opposite signs. Okay. That's all I have to show you. We'll see you in class tomorrow.